All right. So today we're going to solve problem 2601. We about to have a lot of fun. No, prime subtraction operation. Okay, so this problem kind of has three related concepts, okay? One of them you could probably quickly determine just based on the title. We're going to be dealing with prime numbers. We're going to need to understand how to find prime numbers. We're going to need to deal and just manage the situation, which is a prime number. And a prime number, of course, is a number that's only divisible by itself and one positive greater than or equal to 2. Okay? The next thing we're going to have to deal with is a greedy solution, right? A greedy solution is, of course, a situation where you always take what's best for you in that situation. That's why it's called greedy, right? You have a case. What do? I do what's best for me right here, right now. And that turns out to be the best for me overall through the whole problem. And then the third concept we're going to need to use is some sort of binary search in order to determine what is the best thing for us right now in this very situation. So to quickly summarize, we got to deal with prime numbers, we got to deal with a greedy algorithm, and we got to deal with some sort of binary search to utilize our greedy algorithm efficiently. Okay, so boom, boom, boom. Let's go ahead and read the description. So you're given a zero indexed integer array nums of length n. All right. You can perform the following operations as many times as you want. You can pick an index I that you haven't picked before and pick a prime p strictly less than nums of I, then subtract that prime p from nums of I. Okay. Return true if you can make nums a strictly increasing array using the above operation and false otherwise. Okay, a strictly increasing array is an array where each element is increasing strictly, right? So it's getting larger every single time. It's not staying the same. It's not getting smaller. It's continuously getting larger. Okay, so in this example, right, we have an example. We have nums equals, 4, 9, 6, 10. And, well, what do we need to do to make this thing increasing? Well, we have 4, 9, 6, 10. So what are our first couple prime numbers? You should probably have these memorized if you're going to be a mathematician. Well, our first couple prime numbers, right? We got 2, we got 3, we got 5, we got 7, 11, 13. That's where I start forgetting what they are. But, there's our first couple prime numbers. So if we wanted to make 9 smaller, because the problem here, right, is like we look at 6, right? And 6 is not greater than 9, so we need to make 9 smaller. So we could subtract 7 from 9, right? Because we have to subtract something that's smaller than 9. So it would be 4, 2, 6, 10, right? Because we subtracted 7 here. But then, okay, this is resolved. But now we have an issue over here. Right? So that's not going to work. So maybe if we subtracted something smaller like 3, or let's say 5. But if we subtract 5, then we get 4 here. So maybe in order to make this work, we need to start dealing with this one first, right? Because even though this isn't an issue here, like 4, 9 isn't an issue, well, it's becoming an issue because we can't subtract anything from 9 to make it smaller than 6 without making it an issue over here. So maybe we'll make 4 smaller first. So what can we subtract from 4? Well, we could subtract 3, right, to make this 1. Right, because the only thing we can do is we can subtract a... Where's my hand go off? We can subtract a prime that's strictly less than nums of I, right? So any prime that's strictly less than 4 is 2 and 3. So you can subtract 3, that'll make this 1. Now 9, we can subtract a 7, right? And to get 2, and then 6 and 10, and we're done. Right, so there you go. Right, 1, 2, 6, 10. We have an increasing array, and I don't know if their answer is going to be the same, but yeah, okay, it is. So 1, 2, 6, 10. Okay. 6, 8, 11, 12. Okay, it's already ordered, so you don't need to change it at all. 5, 8, 3, it's impossible. Why is it impossible? Okay, well, let's look at the extreme case here of 5, 8, and 3. So for 5, 8, and 3, nums equals, am I on screen? Yes, I am. 5, 8, 3. So, again, for reference, we have our primes here. Our first couple primes, of course, we're going to need a lot of primes, right? But to do this, but, for just a little example here, we can use our little table of, 6 primes. So 5, the smallest thing I could do is I could make it 2 by subtracting 3. Now 8, I might want to make it small as possible and subtract 7, but if I subtract 7, I'm going to get 1, so then I'm going to have the issue of having 2, 1, and that needs to be increasing, so I need to do something smaller than that. So maybe I could subtract 5 from there, right? That would make this 3, and then I have a 3 at the end here, but what am I going to do to make this 3 a bit larger, right? The smallest I can make 8 is 3, and this needs to be 3. See what I'm saying? So we're kind of in an issue here. What am I going to do here? I can leave it as 3, but it's too small. I need to make it larger. The only way I can't make it larger, so the only thing I can do is make the previous one smaller. To make 8 smaller, I have to use 7, but if I use 7, then this is going to become 1, so then I have to make this smaller, but then I can't use any 5 larger 3. So you can see this doesn't work. All right, so this one is a false. All right, these two, the two examples before, those are both true, and this last one is false. Okay, so it's a good array of situations. Okay, so I kind of said that there's 3 parts to this problem, right? I said the first thing is, and always will be finding primes, which I think it's pretty clear now. The second part was a greedy approach. And the third part was binary search. How do these things all play in a role? Okay, I think it's pretty obvious where primes plays a role, right? Because I need to determine what I can subtract something by to decrease it, right? I need to know when I'm looking at 9, like, what primes can I use to subtract, right? Well, then in order to do that, I need to know what the primes are, right? So that's the first part of this problem, and it's pretty obvious. These other two might not be as obvious, but let's first just deal with this prime issue, and then we'll, look into how we're going to solve this efficiently and determine efficiently and what that would look like. But let's just first, piecewise this and look at each thing individually. Okay, so there's a pretty clear algorithm for finding prime numbers. It's efficient enough. And if you notice with the constraints here, right, always look at your constraints, that num's length is less than or equal to 1,000. Okay, so there's only 1,000 elements we're going to look at. But also, the numbers are only less than or equal to 1,000. So each number is less than or equal to 1,000, right? So the max of nums, in any case, given these constraints, is 1,000, right? And each prime needs to be less than nums, right? So our max prime has to be less than the max of nums, all right? So that means that our max prime has to be less than or equal to 1,000, all right? Because we can only subtract out, right? The constraint says here, right? We can only subtract out primes that are strictly less than nums of I, right? So our max prime has to be less than our max nums. Our max num is 1,000, so our max prime is less than or equal to 1,000. So what does that mean? We only need primes less than 1,000. So we only need to know primes less than or equal to 1,000. So here, right, I made this table. Oh, that's from a different problem. I made this table, right, to figure out what my primes were within the range I was dealing with, right? And I kind of just scratched it up. But if all my numbers are less than 1,000, the only primes I can use are primes less than 1,000. So let me just find all the primes that are less than 1,000 and we'll be in good shape, right? Okay, so how do we do that efficiently? Well, there's an algorithm to do that. And basically what you do is you consider all the numbers from 1 to 1,000 prime. And I'm just going to do the first couple here. I'm going to put these dots here to represent, that's the other ones. Okay. And, okay, primes have to start at 2, so you can read this one out. I'm actually going to do it here. Okay. And then when you encounter something, you take it and you say, okay, this is prime because nothing before it was divisible by it, right? 2 is the smallest prime, it's the first prime. And what isn't a prime? A prime is something that's divisible by something other than itself and 1, right? So everything that's divisible by 2 is not a prime. So that means 4 isn't a prime, right? Because 2 times 2 is 4, so 4 is divisible by 2. Everything that's divisible by 2, when you go 2 steps away, it'll account for that number, right? So that means 6, I'm going the wrong way here. So 2, so that means that 4 is not a prime, 6 is not a prime, 8 is not a prime, 10 is not a prime, 12 is not a prime, so on and so forth. And then what I do is after I go through all of 1,000 elements, I look at the next one and I say, has this been highlighted red? No, it isn't. So nothing smaller than it divided it, so it must be a prime. So then I can say, okay, this one is also a prime. And then I can exclude all the elements that are divisible by 3. So then I count through, I say 6 is not a prime, 9 is not a prime, 12 is not a prime. And then I look at the next thing and I say 4. Nope, 4 is red now because it was divisible by something before. So I'm not going to use this one, and I'm going to increase. I look at 5 and say 5 isn't divisible by anything smaller than it, because if it was, it would have been colored red, so it must be a prime. And what does that allow me to do now? Now I can start coloring all the things that are multiples of 5 red. So 5, 10, 15, 20, 25, 30. I play this game again. I increase to 6. I look at 6. I say 6 is red, so it must be divisible by something before 6, so it's not a prime. I look at 7. I say, I've tried all the multiples of things less than 7. It doesn't reach 7, so 7 must be a prime. And then I do things that are multiples 7 away. Right, so basically what I do is I instantiate an array P from the range of the primes that I'm looking for. And all my primes have to be less than or equal to 1,000. So I'll say from 2 to 1,000. All right. I'll start with my first value at 2. I'm not going to do it this way. I'm just going to write the code out. You know what? I'm not going to play this game. But let's see if we can figure out what all the primes are from 2 to 1,000 using this little trick, okay? So basically, I start with all my possible primes, and I'll use zeros and ones. Zeros mean it's not a prime, 1 mean it is a prime. So we'll assume that everything is a prime to start. Okay, and how many are we looking through? All 1,000, so 1,001. Now, we're going to say for possible prime in range 2 to length of primes. Well, if it's a prime still, then the value will be 1 at primes of P. And then we're going to do that multiplication increment factor to color all the things that are multiples of this prime number red, so we know that it's not a prime in the future. So value equals primes at P. And then we'll say while value is less than length of primes, we'll do 2 times P because we don't want to color the prime value itself red, only multiples of it. We're going to say, okay, primes at V now equals 0 because it's a multiple of the prime, and then V plus equal P to increment it, right? So if this was 2, right, we say, okay, 2 is a prime, so the first non-prime will be 4. Then we'd make it 6, then 8, then 10, all the way to 1,000 to account for all the primes. And then to collect the primes at the end, we say, okay, our primes are just the numbers, the P's for P and is prime in enumerate primes if it is a prime, right? Because if it's 1, it'll stay 1 and be a prime. If it is hit, then it'll become a 0 and it's not a prime. All right, and then let's print out the primes, and then let's just return true for now, so it doesn't error out, even though that's going to probably be wrong, or I don't know, it depends on what the test case is. All right, so here, does this look right? Are these all the primes from 0 to... Are these all the primes from 0 to... No, they're not. 1, 3, 5 is a prime. It says it isn't. Yikes. Oh, because this is the value. P is the actual prime number here. So that's why you test your stuff. That looks better. So standard out... Okay, the problem is here is it's saying that 0 and 1 are a prime because they stay as 1. So I'm just going to say primes of 0 equals 0, right? Because 0 is not a prime and 1 is not a prime. So just to account for that. Because we start at 2, so we never have the opportunity to read those values out. So I'm just going to hard code those 2. All right, and here you go. Here's all your primes from 0 to 1,000. Okay, so that's the kind of efficient way of finding your prime numbers. Okay, so now we have those prime numbers, so then how are we going to use them to find the solution? Okay, I am running out of battery. I have 4%. So I'm going to be right back in like 5 seconds. I have to get my charger. This is very unprofessional, but I really have no other option because I don't want to restart the video. All right, so just tell me about your day. Think about this problem. Think about what the solution looks like. You know, think about where the heck my charger is, because apparently I can't find it right now, and that's very concerning. Think about what life is. Like, what does life really mean? You know what I mean? Like, what are we doing, you know, stuck on a spinning rock floating through space, right? Like, is our purpose to Leetcode? Like, how important that is this in the grand scheme of things? Or maybe it is really important to you, right? Are you doing this because, you know, you want a job? Are you doing this because you just like the activity, right? I like the activity, you know. I've always found it fun, and a lot of people tell me, you know, you should probably apply to a big tech company if you're, you know, doing all these Leetcode problems. But I feel like that kind of defeats the purpose of what I'm doing, right? You got to do things because it's the love of the game. If you start doing things because you feel inclined or obliged because, you know, it's mandatory to get a job or whatever, that's when you really start not enjoying what it is that you're doing. So, you know, that's just something to think about as you solve these problems, right? Have love for the game. Don't do it because there's some, you know, cookie or gift or reward that you get at the end of the day, right? Do it because you love Leetcode and you love yourself. And, yeah. So with that said, let's go ahead and continue solving this. Okay, so now we have our prime numbers, right? And we're in good shape in that regard. But now we need to think about how are we going to solve this problem efficiently, right? Because we kind of ran into some weird situations here, right? Like, you know, if we start walking through this, we'd say, okay, this is good and this is good. But then we get to 6 and it's not good. But then we soon figure out, well, it's not good because 9, although 4 and 9 are good, 9 needs to be smaller in order to account for 6. Okay, so where does the greedy approach come into play here? When you have 4, 9, 6, 10, okay, one thing to think about is I'm trying to make this increasing, right? So to make it increasing, I should make 4 as small as possible. And that won't affect anything, right? If this ends up being, you know, our answer is 1, 2, 6, 10 in the end, right? Right, imagine our final solution to this problem was like 7, 10, 11, right? As long as whatever you have here at the first slot is less than 7, you're good. So you might as well try to make it as small as possible, right? Because making it as small as possible increases the chance that the next element can be larger, right? If I want to ensure that my partner is taller than me, I should try to be as small as possible. That way they don't have to be as tall, right? If I make this first number as small as possible, then the next number won't have to get, that the next number has more wiggle room, right? I'm basically giving the next number an opportunity to be larger, or to be smaller. Does that make sense? If I make this first number as small as possible, then the next number has more wiggle room. That's kind of the idea here, right? So, you know, regardless of what you're looking at here, when it says 4, 9, 6, 10, right? Maybe the solution here is to make it 2, right? You can make this 2, what was the answer here in the end? Or whatever, right? But the ideal thing would be to make it as small as possible without breaking the constraints. That way 9 has more wiggle room. So what would be the best thing for 4? Well, the best thing for 4 would be the prime number that's as close as possible to 4, which is 3, to make this 1. And the same thing with 9, right? I should make 9 as small as possible as long as it doesn't get smaller than the smallest thing I already have here, which is 1, right? But I should try to make it as small as possible. That way, this guy has an opportunity to get small, right? So I should make him as small as possible, but also understand I can't make him so small that he's small as the same size or smaller than the one before him, right? And that's good that I made this thing as small as possible because that gives him more wiggle room, right? So I might say, okay, the smallest thing for 9 to be is 7. And does that allow him to be larger than this thing? Yes. So this becomes 2. Now I have 6, and I'm saying I need to make 6 as small as possible. So you might say, okay, 6 goes here for 5. But that would make it 1. So I need to make it small as possible while still respecting the previous element. So I can't use 5, but I could use 3 to make this 3. And then 10. Of course, we're already good, but to have this problem have a consistent approach, right, I say make 10 as small as possible while respecting 3. So the smallest thing is 7. 10 would go here, 7. That would make it 3, though, so I have to minus 5 to make it 5. right? So basically the greedy approach is choose smallest, choose largest prime. So choose largest prime, less than x, still larger than prev. And what do I mean by that? When I look here, right, let's do this again with a little bit more efficiency, a little bit more better stated so we can figure out what needs to go where. Okay, when we look at 4 here, I'm trying to make 4 as small as possible. And my constraints are it has to be less than 4, right? And there's nothing on the left, right? Because there's just a 0 here. So I can choose the largest thing, 3. So I subtract 3 and this becomes 1. Now when I do 9, what's the maximum thing I could subtract? Well, I can't subtract more than 7 from 9. Why is that? Because it has to be larger than the previous thing that's already been made as small as possible. So you might say, okay, the closest thing to 9 is what I'll pick, but really I need to pick the closest thing to 9 minus the difference, right? What's the largest thing I can subtract from here? Well, I can't subtract 9 because then I'll get 0. I can't subtract 8 because I'll get 1. So I have to subtract 7. So the smallest thing I can subtract is this prev value minus 1 from 9. So the smallest thing I can subtract is 9 minus 1, which is 7. To get 2. Now you'll really see it play a part, right? Again, remember, the closest thing to 6 would be 5, right? But I can't subtract 5 because then I get smaller than 2. The smallest thing that can be here is 3, right? So the smallest thing I can subtract from 6 is 3, right? So that's just 6 minus 2 minus 1, which equals 3. And then the 3 goes here. Right, and then again here. So 10, the closest to 10 is 7. But remember, the smallest thing I can make is 10 minus 3 minus 1, right? Because it's the difference, right? Because I can't go smaller than 3. So the smallest change I can make is 10 minus 7. 10 minus 3. But that would, the smallest thing I can, the largest thing I can subtract is 10 minus 3 minus 1 because it has to be larger than the previous thing. To get you 10 minus 3 minus 1 is 6. So then I go here and I see 6. I see 6 and the 5. 1, 2, 3, 5 would be the ideal solution here. Super messy. Maybe when I write out the code, it'll make a little bit more sense. But, you know, the basic idea is I want to choose the prime number. I want to choose the largest prime number that's less than 10, but also doesn't make 10 less than the previous number, right? So I want to choose the largest prime number that's larger. I want to choose the largest prime number that's smaller than my current number, but also not too large that it subtracts from my current element. One moment, I gotta... Okay, so I hope that makes sense. Now, what are we doing? So, I hope that idea makes sense. So I need to find, for 10, well, I need to find the largest prime that's less than 10, but not so large that it makes it smaller than 3. So, or the same size or smaller than 3. So that would mean that the largest prime I can find has to be less than or equal to 6, and that one is 5. Okay, so that's where this idea of the greedy solution is, right? Because I'm trying to find the largest thing less than a certain value. Now, finally, the thing we're looking for here is, where does binary search play a role? Well, binary search plays a role because this prime system is already sorted, right? And what I don't want to do is like linearly look through this whole system trying to find the prime value that I'm going to use, right? When I have 3 and 10, right, I'm saying, okay, the largest prime I can look for this situation would be 10 minus 3 minus 1, which would be 6. So what I don't want to do is manually look through like, okay, is this the largest thing less than 6? No. Is this the largest thing less than 6? No. Is this the largest thing less than 6? I don't know. Is this the largest thing less than, oh, this is greater than 6. That must mean the previous thing was the greatest thing less than 6. No. What we'll instead do is binary search on the system, right? So we have 1,000 primes. We'll drop our number in and we'll binary search to find what is the largest prime less than the difference between, you know, the current thing we're looking at and the difference of the thing before it. Okay. So let's go ahead and do that. So now we have our primes. All right. At the end, we'll return true. Otherwise, we're going to walk through like this, right? So we're going to say our prev is 0 initially. Okay. We're going to look at each number in nums. And we're going to say, okay, the value that we're looking at, right? The subtract value we can use is the prime value when we find the number. So we bisect right of our primes. And what are we looking for? Well, we're going to bisect right of primes of what? Well, it has to be smaller than our current number minus our previous value, right? So remember that 10 minus 3 minus 1, right? That's the largest prime we can use. The largest prime we can use is a prime that makes us as small as possible, right? So the one that makes us as small as possible will be the one closest to us when we subtract it, but also not too small that it's smaller than the previous thing. All right, and then that'll give us the index, so we do minus 1. Now, one thing I'm going to do is add 0 to primes because there might not be a prime that exists, right? We might go all the way to the left, right? We might have no prime that's smaller than us, right? What if the value is 1 or something? There's no prime smaller than 1, so you can't subtract anything. So we'll keep that 0 here, even though 0 technically is not a prime, okay? And then we'll run through this situation. So that would mean that our new element's value would be the current element of I minus, what I call it nums of I num. So num minus the sub value. So I'll just call that prev. That'll be our new prev. Equals num. So I'm finding out what our new prev value is, right? Because I take 10 and 3 and I find out that the smallest prime I can use, the largest prime I can use is 5. So then I do 10 minus 5 to get 5, right? So that's what this is. And how would I know if it didn't work? If I did that subtraction and the prev value, the new prev, is larger or equal to prev, so I subtracted the best thing I could to make this as small as possible, and it's still smaller than... Basically, I took the system, I did the ideal thing I possibly could, and it still made it so that my value was smaller than the previous thing. I have to return false. Otherwise, this is our new prev. Oh, no. Oh, no. If prev is our new value, so... Flippy flop. All right, let's try that. Let's cry because it doesn't work. All right, cool. Okay, so let's do n is the length of nums. For time, well, we have to look at all 1,000 primes. I don't know what the runtime of this is. It's like 1,000n or something, but it's constant because we're only looking for 1,000 primes, right? So no matter how big our system is, we only look for 1,000 primes. So that's 1,000x something. I don't know what the runtime is, but it doesn't matter. And then for each num, we look at all n nums, and then we have to do bisect on the prime. So that's log of the number of primes. So we'll just call that log of n, I guess. Ugh. We do the bisect on the primes, and the prime size is less than 1,000. It's constrained. So it's really n time log of something. Someone in the... And then we have to make this 1,000 space. And then we just set these two variables. So that's constant space. But again, it's the number of primes. So let's just call p the number of primes. And that's constant, but it's a variable that's the same. It's a constant through the whole thing. It doesn't matter about nums, but it is a big variable, so we should account for it. Right? That's why time complexity analysis can be kind of tricky sometimes. But it's definitely n log p. And then the operation of this is a little weird because we do p operations, but then like I think this is a log p system because you're incrementing by p. So I call it p squared. It could be better than that, but just say for the sake of argument, that's p squared. For space, we have to have all the p primes, and then we do constant operations. Okay. All right, guys, that's it for today. I hope you have a beautiful rest of your day. Peace out.